Not going to use microphones then. So, start off, my name is Chris Girth. I'm a software mentor on Team 1736 Robot Casserole.
I'm Aaron. I'm an alumni of the team.
We are here this morning or this afternoon, just barely, to talk to you guys about a software algorithm we did in 2016 to help prevent brownouts. So, over to you, Aaron.
Okay, we're talking about battery load limiting. The quote here is just a reminder that the model that we're going to be talking about is by no means 100% accurate, nor does it need to be. You don't really need to care about everything on the robot, just as long as it's useful. So a brief introduction. If you don't know what a brownout is in this discussion, we're going to be talking about what they are, why you care about them, specifically why you don't want them, and then we're going to talk about our results of using our algorithm, and maybe that'll be helpful for you. So there's some math ahead. There's not a whole lot, and we're going to try to get into some hand-wavy explanations. We have a formal paper that's on Chief Delphi, or you can contact us or something if you really want to read it. You should probably have a basic understanding of physics, but it shouldn't be too bad. So basically, what's a brownout? It's when your component shuts down, or your component shut down on your board due to low system voltage, unexpected drops and things like that. Causes can be a dead battery, an old battery that's inconsistent, or if you're trying to draw too much current from it, it can also cause brownouts. These are really bad because they interfere with the functionality of your robot, what you would expect it to do. So we really want to keep them to a minimum. Brownout, the concept of a brownout, I guess, is present in basically every electrical system that is prone to voltage drops. They're newish on the RoboRio. They exist on the Serio and older systems like that, but the RoboRio introduced a staged brownout protection system, which has set values for which things happen. So when the system voltage is less than 6.8, then your motors and servos turn off. Those are the biggest load-bearing components, or load-causing components. And when the system is less than 6.3 volts, then we remove it from SPI and I2C devices. And then if it's less than 4.5, that's really bad. You really don't want that to happen. Your Serio is going to reboot. So there are solutions to problems incurred by brownouts. Physical, mechanical solutions, fewer motors, have a less aggressive drivetrain, just reduce your load as much as possible. Or like wheel modifications, make it slippy, more slippy, so you're not inducing as big a load in that regard. But you might not want to compromise, so we did a software solution. It was helpful for us, but it requires a little bit of tuning type of stuff. So for this, I'm going to be talking specifically about the battery component and how to parameterize your batteries. So the model that we're using is basically a linear model. This isn't strictly accurate, but in a localized sense, if you're assuming that these values don't change that much, then you can have a linear model. It's not too big a deal. So batteries, we know they convert chemical energy to electrical energy. We have our voltage of the open circuit, our VOC. That's probably about 12 to 13 volts in a healthy battery. But we have some internal resistance when it's hooked up to components. That's that changes with time. It changes with the age of your battery. During the length of a match, it changes. So we need to be able to model this and update it continually while we're executing our algorithm. This is pretty important because our system voltage is really what we're concerned with. If that drops below our thresholds, that's when brownouts occur. We need to reduce that, or prevent that, really. So if we can predict or foresee a voltage drop that would cause a brownout, we need to stop that. We need to step down a voltage our voltage commands to our motors and things like that. So there's multiple things that we have to do. So we have to characterize our battery. We have to figure out what our VOC is, our voltage of the open circuit, and our RBAT values for a particular instance of where we're trying to make a voltage call. And so once we have these, we can start characterizing our battery and we can prevent the behavior from happening. So the first thing is we have our open circuit voltage and our internal resistance. When the voltage drops, the resistance slightly increases. This is pretty basic. It's Ohm's law type stuff. And I forgot to mention, I guess, our linear model comes from Kirchhoff's voltage law. Everything in the system can be added up together, work together. It's fine. And when the load gets bigger, our system voltage will dip by a lot. Let's see. So the two values that we're concerned with is our open circuit voltage and our R battery. Those are the values that we're going to be parameterizing. So basic algebra, slope-intercept form. Like I said, in a localized sense, we can get values for our voltage and our RBAT, and we can assume them as constants. And in this sense, they're basically constants. But if we have values for our system voltage and our VOC for our battery, then we can calculate our battery resistance and our load. And so our system voltage and our current can be measured from the power distribution panel. But if you try to measure it directly, like when you're trying to make a call to your motors and try to power them, that causes problems because it's a delayed response. And so basically you're commanding the voltage and then seeing what happens. And you can't prevent brownouts by that, you can just observe them. So what we need to do is we need to characterize these and make a model just so we can approximate what happens before we actually call issue a command to our motors. What we do is we look at previous values. We assume that these values don't change that often. Our system voltage, they're slow changes. So if we model, or if we store the values of these pairs beforehand, then we can use that in our approximation to see what would happen to the system voltage on motor current. And so this is kind of what it would look like in slope-intercept form. We have our values for system voltage and system current, and we can model them in some linear fashion. And this is probably a more accurate representation. There's changes it's not strictly linear. There are changes in values, so they kind of exist in a cloud around this line, and we're modeling a best fit line rather than a perfect fit. But the slope of it is your change in battery resistance, which is kind of what we're concerned with. But if all of the values are close together, so this might happen if your robot is sitting still, it's a stationary position, nothing's really changing, then you kind of exist in a cloud that's really, really small, and it's hard to find a best fit line. So in that specific case, we just kind of hold the last good value for our algorithm and just assume that not much has changed. And so what we care about is, if you don't have to remember everything that I specifically said, but we can remember our voltage and current, we can model a best fit line, and we can use that along with what Chris will tell you to approximate our motors, or what our voltage drop would be.
Cool. All right, so I'm going to take over here for part 2 of our 3-part quest, I guess. So part 1, we were going to figure out parameters that describe how our battery will behave under load, and we were able to use best fit lines to figure that out. Part two is we have to be able to find a way to predict, given a certain voltage that we're going to apply to a motor, how much current will that motor draw out of the battery. So that's what we're going to go through here. So similar to batteries, motors they're an electrical device. Their job is to convert electrical energy into mechanical energy. There's two big components to this. Primarily, you apply a voltage to a motor, and some amount of current flows through it. The more current that flows through it, the more torque you get at your output. So for like an aggressively geared drivetrain that takes lots of force to get going, that's why you'll have high current draws for it. There's also this additional effect that turns out to be more important for predicting current draw out of a motor. It's called the motor counter electromotive force, CEMF. What this is that when a motor starts turning, there's a voltage on the inside of the motor that gets generated opposite to whatever you apply to it. You guys have probably heard that motors and generators are kind of the same, or they're interchangeable. The truth is, at least in this model, they are acting as both a motor and a generator at exactly the same time. As soon as you start getting motion and rotation on your motor, that's when the internal voltage builds up and starts to push against whatever you're applying to it, and that's what brings your current draw down. Sure, actually, that would be great. So, as a quick overview of the effects of CEMF here, the bigger your speed, the bigger your internal voltage is going to be pushing back against what you apply. The bigger your internal voltage is compared to what you're applying, the lower current draw you're going to have. And then the other kind of side note to this is that regardless of what speed you're going, if you just lower your current or your applied voltage, the amount of current going through the motor will also decrease. Next slide. Here's a quick graph of this. We did some theoretical calculations for a sim motor on it. More or less all this is showing is just that you have your current draw along this axis and your motor speed along here. If you want to reduce the amount of current going through a motor, you have two options. Decreasing current is this way, so you can either let the motor speed up, which brings you downwards along this line and decreases your current. The other option is you just decrease the amount of voltage going into the motor, which pulls you backwards along these lines down here. Each one of these lines is a different applied voltage. Go ahead, next slide. So, for actually estimating the actual number of amps that will be going through your motor, you're going to need a couple things. There's two constants, the motor resistance and something called the velocity constant. These can both be calculated from numbers that are in the data sheet, if the data sheet doesn't give you them already. The white paper has a sample calculation of how to do that for a sim motor if you're interested. These two things will not change. These are just constants for whatever type of motor you're using. Additionally, you need two measurements. One of them is the motor's speed. So this is the actual speed that the shaft is rotating at in the motor. Presumably you have some encoders on whatever mechanism you're working with, and you just have to do a little bit of math to get that to figure out what the actual rotational speed is. And finally, you will also need to know the voltage that is applied to the motor. Ideally, you know this in software. This is the command you're about to send out to the motor. Two parts of this. Obviously, if you have these numbers, you can just kind of calculate it. And the key differentiation is saying that in software, I know what the driver or the PID algorithm or whatever is commanding me to do. So I know what this is going to be, this motor voltage here. If I presume that from the instant before I apply the command to after it is, the motor speed's not going to change much, my motor speed just remains whatever it is right now. You do your arithmetic on the side, and you get out the actual number of amps that will be flowing through that motor if you apply exactly what the driver is telling you to do. Next slide. And that actually, in and of itself, is exactly the predicted current that you're looking for. So all you then have to do then is you perform this, this prediction method for every single motor on your robot that is big enough to cause a big current draw. And then you just add them all up, and that becomes your predicted system current draw, the predicted draw of what's going to be pulled out of your battery that's going to bring the system voltage down and eventually cause a brownout, potentially. Kind of side note here, for 2016, Casserole was able to assume that the drivetrain was the only thing that actually mattered on the robot. We didn't have any other big mechanisms, but if you've got something like, 5 motors on a shooter or something like that, you might want to accommodate for that as well. So that is part 2. We've calculated a theoretical system current draw. Next slide. In part 3, finally, we're going to put it all together and prevent some bad behavior. So remember back to our initial equation we started off with. This is the system description of how our battery is going to drive a system voltage given the amount of load you're putting on the battery. Go ahead. So these two parts are what Aaron talked about, your open circuit voltage and your battery resistance. Those both were calculated as part of part 1 through the best fit line method. The system current is what I just described over here with your motor speeds and the intended applied voltages. You can predict what your system current is about to be. Again, just do arithmetic on that side, and now you're back. You have a predicted system voltage of what's going to occur if you take no action to correct what the driver is doing. Given the system voltage, then it's just a pretty simple question you have to ask yourself in software. Am I happy with what the system voltage is? If it's 10 volts, you're probably okay. If you're getting down towards 7, you might want to do something else. If it's not okay, go ahead. You got to do some sort of limiting. Unfortunately, this is very application specific. If you're able to make the assumption that your drivetrain is the only significant thing that's pulling current out of your battery, it is pretty straightforward to be able to simply say, yeah, just apply some fraction between 0 and 1 to my driver commands and scale them back. That'll get you there, and that's all we ended up doing. You may have to do something more advanced if you've got a bunch of mechanisms and do something like a power budget to say, this mechanism, we take all the power away from it first, and then we take away from this one. There was a method proposed by 254 for doing something called LQR estimation. If you want to put all this into a matrix, there are mathematically rigorous ways of determining that, but again, if you're able to just know it's just your drivetrain or something like that, you can take a much simpler approach. Yeah, and that is pretty much it. Once you've determined that limiting factor, all you have to do is apply that to your drivetrain commands, and because all the other math that happened beforehand, it will keep your system voltage high enough. Mostly. There are a couple real-world implementation things to think about. So far, the math we presented has all been extremely, extremely theoretical. There's a lot of resistances that are in various spots on your system. So, the wiring between your motors and your batteries, the main power circuit breaker, all those are going to have various levels of resistance. And we did find when we implemented this that we needed to account for those. If you have good enough instrumentation equipment available in your lab, because you have some really nice sponsors, you can use that to try and measure the resistance of your various components in your electrical area, your electrical system. However, the way we did it was we just plotted out what our estimated current was doing as we actuated our drivetrain different ways, and we compared our estimated values to some actual measured values we had, and then just kept tweaking the estimation resistances until the estimated matched the actual we were measuring off board. Some of the math does presume slowly changing signals, as Aaron did hint at a little bit. We do have to be careful that you don't have any major step changes, otherwise some of our linear models do tend to break down. The other big thing too is that we did end up applying a lot of filtering on those system voltage and system currents to get the noise out of there so we could get an accurate battery resistance estimate. The white paper goes into a lot more details as to where that limiting or where that filtering had to be applied at, for our case at least. But kind of coming back to our initial quote, was it good enough? All models are wrong. We know ours is wrong, but was it useful? Go ahead. I believe the answer is yes. So I only have one slide for results. Go ahead. This is, that's hard to see. Okay. Hopefully you can see at least a little bit of here. So what we did was we ran an experiment on our 2016 robot where we rigged up the algorithm to be able to turn it on and off. We started off by turning it off, so there was no limiting applied to the driver commands. We started running the robot at the fastest we could make it go in forward reverse cycles. So drive as fast as you can forwards, jam the joystick in reverse, go back and forth. And fairly extreme, some of the worst case loading we could put on the drivetrain. And after a short period of time, we started to get a bunch of brownouts. Every time we tried to turn that drivetrain around, we were putting a bunch of load on the battery, the RoboRio would start to brown out the system. And you can see each one of these 3 lines here, as time goes on, this is 100 seconds of data. So as time goes on, you get less and less and less nice behavior. The brownouts are starting to happen every time. What happens right here is we stop the robot, and we flip the switch to turn the algorithm back on. And the brownouts just cease right here. This is the algorithm running and preventing brownouts. Go ahead and hit the next slide. What we had in the software was a limit to say our lowest acceptable system voltage from the end of part 3 is 7.5 volts. And that is exactly where the algorithm was able to keep us at. So yeah, admittedly that went a lot faster than I thought it would. Go ahead. But that is all the prepared material we have. Again, this was kind of intended as just kind of a quick overview as to the math that we were able to do. The full mathematically rigorous proofs and derivations are all in our white paper on Delphi if you want to go find it. It's got some of my contact info in there as well, I think, so not let it in. So if you want to talk to me or Aaron about any of this, we can. Quick special thanks to our sponsors, Caterpillar, PTC, the Peoria Police Benevolent Association. They're the ones who definitely help make this kind of thing a possibility every year. And as well as we had a couple of good content reviewers, Jeremy Lee from Crimson Robotics, Larry Schmidt from 1736, and the infamous Ether from Chief Delphi. So I guess I'll open the floor since we do have plenty of time left. If anybody's got any questions and we want to go over anything again, talk in more detail about any parts of the algorithm. Yes?
So in your algorithm, you calculated that, well, you said you calculated if the driver applies to this particular speed, it's not okay. So you didn't go into, okay, now how do we calculate what is okay?
Gotcha. Yes, that was part of the intended hand-wavy part. So
go back to your
sure, go back. So this is so this is the limiting factor, or this is all we had on here. So there are two ways to approach this. One way is to basically take all the math we described and do it in reverse. You back calculate to figure out, given where my current battery state is, what is the maximum motor command I can apply that will still prevent brownouts. That math, what we found was it got kind of complex, mostly because the speed controllers kept introducing absolute value signs into your current calculation. Just because, when you go forward, especially when you account for the forwards backwards case. So you can do the math, but what we basically got to is I'm not 100% sure how to interpret these results. So we did a simpler method where we had this implemented currently in a function call that just says, given what our battery's at, and here's the motor commands you're about to apply, what's your system voltage going to go to? Which is a quick iterative solver, 10 iterations max to find what limiting factor would actually get us the right results, or what's the biggest limiting factor that would get us the results. So we just started at, basically it's 9/10, 8/10, 7/10, and just kept going down until we found the biggest number that would still satisfy our constraint. Does that make sense? Yes?
In characterizing your battery models, did you try multiple batteries, and did you find any that performed better than others?
Yes, in general. So the raw data we get back of the battery resistance and the open circuit voltage stuff, it is fairly, it's the mathematical description of how well a battery is going to perform. In general, what you would probably care about over the course of the match is how quickly is your battery going to degrade. So, from your start of the match, you have a certain resistance in your battery, and towards the end it goes up. How much does it go up? I'll admit we never actually analyzed that for our batteries, but we do have all of our data logs from our robot last year that, if we wanted to, you could go back and post-process to basically say, if you knew which match was which and which battery was which, you could see differences there. And we definitely saw, every match you could clearly see the resistance would go up. And especially while we were doing practicing with some of our older 2014 and previous batteries, you could see the resistance would do this for a good battery, and it would go way up over the course of the match for an older one. So yes, from the characterization, you could determine that.
In most cases, if you're not using old batteries, you're fine.
Yeah.
Yeah, I was really interested in differences between models that were legal for FRC.
So so we are doing the, did I put in there MK18, I believe? I might have that model number wrong. We use basically all the same ones, so we are in the same, we do not have any information, unfortunately, on differences in models, but that would be something you could get with this.
Obviously you're not taking into account the step type of thing. So from last year, that's a pretty good example. One of the areas that we found that killed us was that they call it the brick wall.
Yeah. You run into the wall, you got a very sudden load on your motors.
You would hit a steady state, and then it would hit the wall.
I got you. So you got your motors running.
Step slam.
Right. So. Yep, okay, I gotcha. So we didn't have issues with that we saw at least. In that case, what I would expect to happen is, as you make contact with the wall, your wheel speed is not going to immediately drop to 0. You're going to get some amount of ramp down, which hopefully would be measurable by the encoders. And as long as it's not an immediate drop down of speed, and your encoder signal is not delayed either, that's a big portion of it, as long as you can accurately track your wheel speed as it goes down, the algorithm should be able to cut in, even with the same battery parameters, and be able to cut in and say, your motor speed is going down, therefore the maximum acceptable applied voltage to the motor should also be going down at the same time. And I guess the presumption there would simply be that A, your encoder signal is not delayed by a ton, because if your wheels actually slow down before you can measure it, then this algorithm can't help you. The other part of it too would be making sure that if you do have a sudden step change in your motor speed, I guess it might work still in that particular case, but I would be a little concerned about just having a sudden step change. That's going to introduce different things into the system and how the battery is going to be able to respond to that are probably not captured by our battery model.
So you were okay, the Robo-Rio was working at 20 hertz, so you saw that the sampling rate was fast, right?
Yes, so more specifically, the critical, for the encoders at least, yes, we did see that was running fast enough. We were at least at a 20 millisecond loop, which I think is faster than 20 hertz, or it should be faster than 20 hertz. So we were running a 20 millisecond loop for doing this.
Yeah, 50 hertz.
50, yeah. So yes, that was sufficient, and reading the encoders directly into the Robo-Rio, not through like a Talon SRX over the CAN bus. That would give you a little bit of extra delay. But. Cool. All right, well, I'm going to stick around for the full hour. If you guys got any questions, feel free to come on up. But thank you very much for attending. Check out the white paper if you're interested, and by all means, feel free to PM me on Chief Delphi if you guys are trying to implement this, running into any issues. By all means, I'd be happy to chat about it. So, thank you very much, guys.